Hello students, in this session
Let us solve a question on bending stresses. This question is again combined data question where there are two questions for the given statement, and this is the question of combined bending and torsion. There is a machine frame. Machine frame is given to us at which the loading is like this, right? 600 Newton load is applied in Z direction. This is our Z direction basically. So opposite to the Z direction means it is the negative Z direction. The 600 Newton load is applied. So we have to find out the normal and shear stress at point P. Normal and shear stress at point P. This is the point. This is the point where we have to find out the normal and shear stress. This we have to find out for this structure where there is force is applied 600 Newton, a horizontal force, right? So this is the first part of this question. This question was asked in GATE 2007, and when the load is applied eccentricity, so there will be torque as well as bending moment will be acting on this machine frame, right? So we have to analyze both bending stresses and shear stresses due to torque and bending moment, right? So let us solve this question.
in this question we have a frame like this at which a machine frame is there at which a 600 Newton load is applied in this direction. This direction is Z direction. Basically in Z direction we are applying the 600 Newton load, right? And we have to find out the stresses, the normal stress and shear stress developed at point P, right? So this question is basically the combined bending and torsion question is there, right? How it is combined bending and torsion? When this 600 Newton load is applied, it will like to twist. It will like to twist this frame in anti-clockwise direction in this direction, right? So you can see here due to that twist, the shear stress will be developed here in the material at point P, outer fiber, and also you can see here when 600 Newton load will be applied here, then it will try to bend this, if I make a different diagram of this, some simpler diagram I am making. The combined effect of 600 Newton I am applying here at point at this point. Suppose this is a point. So what is the combined effect of 600 Newton? It will be combined effect of point load as well as a twist, the torque, right? So if I make a combined effect of this, this I am making this, right? And this point is P. This point is P, and reverse the direction now. This is Z direction, this is X direction. So this is the X direction. Now I have made this direction as X direction, and Z direction is now same. Z direction is there. This is Z direction, and this is Z direction, this is X direction, and this is Y direction. This direction is the Y direction, right? This is Y direction. So Y, X, Z direction, right? And 600 Newton load is applied. 600 Newton load is applied like this. 600 Newton load is applied. This is Z direction because 600 Newton is applied in Z direction. So this is Z direction and this is X direction. So 600 Newton load is applied opposite to the Z direction. This is Z direction and this is opposite to Z direction, and this is X and this is Y, right? And when this 600 Newton load is applied, it will try to bend this point P, right? So that there will be tensile stress. You can see here this bending moment is such that there will be tensile stress developed in this outer fiber. At this outer fiber there will be tensile stress developed, and this lower fiber there will be compressive stress developed, right? And there is a twisting moment also. That is, twisting moment is 600 multiplied by 500, right? So torque will be applied that in anti-clockwise direction, which is 600 multiplied by 500, right? So there is anti-clockwise torque is there like this. So this is the torque which is equal to 600 multiplied by 500 Newton millimeter, right? Or 0.5 Newton meter, right? You can write 600 multiplied by 0.5 Newton meter, right? So this is the combined effect of 600 Newton load, that is torque 600 multiplied by this, that is the torque. Trying to twist this, that is we have written 600 multiplied by 0.5 Newton meter, that is the torque. And when this 600 is applied in z direction we have made here, so this is in z direction, opposite to z direction. So there will be bending moment, developed, and the bending stresses will be developed, because it will act like a beam now, right? So this is the question of combined bending and torsion, right? So what will be the bending moment at point P? At point P, and at point P there will be tensile stress developed, right? So what will be the bending moment at point P? That is the 600 multiplied this length, and this length is this length, this is 300. So this length is basically 300 millimeter. 300 millimeter. 600 multiplied by 300. This is the bending moment. So this is load multiplied by the distance. So this is 600. Also you can draw the bending moment diagram and find out the bending moment here, or you can directly see that it is a cantilever beam and the load at the fixed point will be this 600 multiplied by the distance. So it will be 600 multiplied by 0.3. So this will be equal to 180, and this is Newton meter, right? Newton meter, right? So this is 180 Newton meter is the bending moment applied at this point, right? So due to this there will be bending stresses developed, and what will be the bending stresses? You know that bending stresses will be maximum at the outer fiber and minimum at the outer fiber and minimum as the 0 at the center neutral axis, right? So these are the bending stresses. These are the bending stresses. Sigma B, it is tensile upward and compressive downward. In the lower fiber it is compressive, upper fiber it is tensile. So these are the bending stresses developed, right? So we can find out this by bending equation. What is bending equation? That is M by I equal to sigma by Y equal to E by R. And we want to find out at P point, which is at the outermost fiber. So Y will be the radius of this that shaft, right? So sigma can be found out using My by I. So that will be equal to M. M is known to us, that is 180. If we want to find out in millimeter, then 10 power 3 multiplied, right? So that the answer may come in megapascal. Y is the outer radius, that is this. Y is this outer radius. This Y is basically the radius of this shaft, that is 15 mm. So this is 15 divided by I. I is the moment of inertia of a, it is a cylindrical, so moment of inertia of a circle, right? That is pi by 64 d to the power 4. So that will be pi by 64 d to the power 4, and d is 30. So 30 to the power 4. So answer will come in Newton per millimeter square or megapascal. So stress, bending stress at point P will be equal to, solve it and you will get the answer, that is 67.9 megapascal. 67.9 megapascal. These are the bending stress. This is the bending stress in the at point P, bending stress or normal stress, right? Normal bending stress at point P. Next we have to find out the shear stress. Shear stress. What is shear stress? How to find out shear stress? Shear stress is due to this torque applied, that is 600 multiplied by 0.5 Newton meter. So also the shear stress varies due to torsion. The shear stress varies linearly, and it is maximum at outer fiber and minimum at 0 at the neutral axis. So the variation of shear stress will be again same like this. Shear stress variation is again similar to the bending stress like this, right? So this is the shear stress, right? This is tau, and at outer fiber this will be tau max. maximum shear stress will be developed at the outer fiber and zero shear stress at the central point, right, where the neutral axis is there, right. So shear stress will be there, and shear stress can be find out from the torsion equation. What is torsion equation? That T by J tau by R g theta upon L. L is the length, which is 300 millimeter. So from here tau can be find out. Tau at point P will be equal to TR upon J. R is the radius. So torque is 600 multiplied by 0.5, that is twisting moment, that is 600 into 0.5. So this is 600 multiplied by you can write 500 in millimeter multiplied by R, radius is 15 mm, divided by J is the polar moment of inertia. Polar moment of inertia of the shaft is pi by 32 d to the power 4. So this is pi by 32 d is 30 to the power 4. Use it, solve it and get the shear stress at point P. Use the calculator and you will get the value as 56.6 megapascal. So this is the shear stress at point P. So these are the two answers. One is 67.9 and another is 56.6. And which is that option? So answer is option A. So this is the option A. This is the answer, right? First part of this question.